right. Going to go ahead and move on into chapters 2 and then 7 for this unit. And what the focus is here, what we're really going to be looking at to start with, is a lot of the fundamental theories and ideas behind how chemistry works. What are atoms? How do they bond together? You know, how do we name all that stuff? Why? A lot of the sort of why questions. So this is, in many ways, sort of high-level theoretical stuff, okay? So we're going to do a bunch of sort of theory for the next unit or two with less sort of applied math and things like that. It's a lot of concepts, a lot of memorization, okay? But it gives us a good foundation for moving forward into sort of the rest of the class, which is in many ways an applied algebra situation, okay? So sometimes this is more difficult or more complex stuff because people find it difficult. The theory, the ideas, you have to visualize stuff in your head a lot more. So hang with me here and we will get through this stuff that you need to know. One thing I would strongly encourage you to do is to take notes, okay? Whether that is you take a blank piece of paper and you take down notes, whether that is you use the lecture notes and you note, right? Add notations on here of the things that you have questions about, put down your own little questions and things like that. Strongly encourage you to do that, okay? So this is, the lecture notes are essentially the sort of outline of what we're going to cover. This is the sort of whiz-bang audio-visual presentation, okay? So you need to process this material as we're going through it to have your best chance of getting it to stick. So what we have here is we've come upon Jane, who has just received an atomic energy education kit. These were actual kits sold in the 1940s and 50s that actually had things like uranium and other compounds in them that you could buy and use. They were for kids to play with and stuff like that. It's pretty cool. Not as much. People didn't fully understand the dangers associated with the radiation. Not to say that this kit was super dangerous, but it did have fairly significant amounts of radiation in it. But you could do a lot of really cool stuff with that too. So, of course, Jane's father, the chemist, is very concerned and wants to make sure that Jane really has a good grasp of atoms before she starts playing around with the radioactive atoms. Needs to understand the nucleus and the electrons, okay? Concepts that you've heard before. We're going to take sort of a deep dive here. Just before we jump into sort of the heart of the matter, so to speak, of the nucleus, we need to understand a little bit about the development of atoms. Where does this concept, this idea of atoms, our models that we use, where do they come from? So a little bit of historical context about the models that we use to understand what's going on, okay? Science is fundamentally about creating models of the way the world, the universe work. And those models can be mathematical models. Those models can be sort of theories that just describe how things behave. And people create models before science. Those models were tended to be based on logical thinking or superstitious thinking or all kinds of manner of different things, okay? Science really moves that into the realm of trying to gather evidence, to take measurements and use those measurements to understand what's going on. But the foundation of some of our stuff comes from much earlier, much before scientific method and the ideas about how do we rationally look at the world and use measurements to explain what's going on. In particular, a lot of Western culture, of course, is founded on Greek and Roman culture. And the idea of atoms, of pieces of matter that are the smallest, and that's essentially what atoms mean, the smallest. Indivisible, smallest pieces of matter that you can't break down any further, comes from a Greek philosopher, Democritus. And Democritus comes up with the concept of atoms and the void, so that all matter is made up of tiny particles and empty space, which is actually not a bad representation for the way that the world around us is actually constructed. Now, Democritus didn't have any measurements or didn't understand, why. These are just sort of theoretical ideas. It wasn't very popular at the time. Plato and Aristotle's ideas around continuous matter, that you could infinitely divide a piece of matter is smaller and smaller indefinitely, were more popular with Greek culture. The idea of running into something that you couldn't split in half was not exactly a idea that people run into in their daily lives. So, the idea of atoms in the void is sort of the start. There's obviously this sort of big intermediate time between, early BC and around the late 1600s, when the inklings of science begin to start to show up. The idea of actually looking and making measurements and observing the world around us and using that as the basis. And lots of stuff happens in that time frame between the Greeks and sort of the Renaissance. And you've all studied lots of these different periods of history. In particular, the foundations of chemistry come from alchemy. Alchemists were experimentalists. They conducted experiments. What they didn't do was they weren't super good about very rigorous measurements and sort of understanding the more fundamental ideas. There was still a ton of superstition folded into the work that they did, into their concepts and their ideas. But it is around the end of that period, sort of the late 1600s, when we begin to get the start of science, the start of the scientific method, natural law, natural science investigations. And for chemistry, one of the earliest guys is a guy named an English chemist named Robert Boyle. And at the time, all of this work was done by sort of the rich white guys who didn't have to work, and so they would dabble in natural science and natural philosophy, as they would call it. And so Robert Boyle spent a good deal of time playing with gases. He would compress them, and he would heat them and cool them and see what happened. And he came up with a series of mathematical laws that you can use to describe how gases behave. He also did quite a bit of work looking at how our substance is composed and what are different substances made up. One of the things that he did that sort of our next step along the path to understanding how atoms behave is he really came up with the idea that if you have a sample of a substance, they have the same composition. Okay? So if you have a sample of hydrogen and oxygen, all the hydrogens seem to have the same composition. All the oxygens seem to have the same composition. And when you take a sample of hydrogen and oxygen and light it, the hydrogen and the oxygen react together to produce water. And all the water molecules seem to have the same composition. And all the water molecules, if you weigh them, have a sort of ratio between how much hydrogen and how much oxygen. Okay? Laws of definite and multiple proportion. Laws that come from the work that Boyle did that stimulated some guys, Antoine Lavoisier, French chemist, tax collector, and his wife, who was pretty instrumental in the work that they did, in 1789, and Joseph Proust, back to England, who came up with what we call the law of definite proportions. That is that the oxygen-hydrogen ratio is the same for all water molecules. In addition, there's a lot of research going on. These works are finally beginning to be disseminated. They are published primarily in Latin. They are spread around the continent. into Italy, France, Denmark, England, all these places, lots of different people sharing ideas, working together to build a body of knowledge, to come up with a system, work out a way that they can figure out how the world works, okay, the system of the world, so to speak. Sort of the signpost marking the, here we have atoms, here we understand what's going on, is the model developed by a guy named John Dalton. In 1808, I mean, that's how recent sort of this stuff is. It's, 200 years. It's not really that long ago. John Dalton came up with a system, a statement of principles to describe how matter behaves. What are atoms? Okay? And so Dalton says that there are sort of four postulates, four ideas that are supported by evidence about how atoms have to behave. Number one, elements are made up of tiny particles. Okay? We call atoms. Number two, atoms of a given element are identical. All the atoms of the oxygen are the same. All atoms of gold are the same. Those atoms are different from each other. The oxygen and the gold, for instance, are different in some fundamental way. He doesn't know how they're different yet. Okay? But they are different. Internally, everything that we call the same element has the same characteristics. Different elements have different characteristics. Number three, chemical compounds are formed when elements combine together. So if I took hydrogen and oxygen and combine them together, I'm going to get water. The water is always going to have the same ratio of hydrogen to oxygen. By mass, it's going to be a 1 part hydrogen to 8 parts oxygen by mass. Okay, that doesn't tell us the ratio of the atoms, it tells us the ratio of the mass. The atoms, those chemical reactions, postulate number 4, the chemical reactions that we're talking about move atoms around, change how the atoms are hooked together, but they do not change the nature of the atom. I can take that water molecule that I made from the hydrogen and oxygen, and I can do stuff to it. In particular, I could put electricity through it, and I'll get back out the hydrogen and the oxygen, and they'll be the same as they were when they started. The atoms don't change when they form these new compounds. Compound atoms is what they actually call them. When they form these compounds, the atoms don't change. They just, by hooking together in some way, by combining in some way, change the behavior of the whole thing. Because hydrogen gas and oxygen gas clearly have very different properties than water. So, this is a sort of revolution. Lots of work is done, stimulates a ton of research of scientists looking at lots of different aspects of this kind of thing. In particular, how indestructible is an atom? Can we really break it apart? What is it made up of? Right? We have atoms. What makes one atom different from another atom? Guys like Avogadro, Amadeus Avogadro in Italy, come up with some laws that say, hey, look, the atoms clearly have different masses. We can go through and we can find out the masses of lots of these different elements in relationship to one another. Find out that oxygen is 16 times heavier than hydrogen. Okay? Find out that carbon is 12 times heavier than hydrogen. We can look at how can we try and probe what's inside these atoms, okay? And in particular, the new ideas around electricity are very useful in doing some stuff to these atoms that creates some interesting results, okay? So 1897, a guy named J.J. Thomson. J.J. Thomson playing around with what are at the time called Crookes tubes. Okay? And these Crookes tubes are devices that are useful for exploring how matter interacts with electricity. Hold on just a sec, and I'll go get one. So here we go. J.J. Thomson was using something like this. This is an example of a Crookes tube. We have two parts of this. We have two metal electrodes. You can hook up a high voltage source here and here. And what happens is you get some parts, you get some particles streaming off of one end, okay, and shooting out towards this end. Although it took a long time for them to figure out what was going on here. What's really happening, what you really see is a sort of glow that suffuses on this side. You get sort of a greenish glow that happens here if you hook this up. It also kicks out quite a bit of X-rays, so we're not going to do that right now. Now, Thomson does a whole bunch of stuff to study this. They bring magnets nearby. They put other electric fields. They put a target, okay, to see what happens to these rays, what were called cathode rays at the time. How they behave when you do all these different things to them. And the results of this, the fact that it leaves a shadow, the fact that if you bring a magnet, it bends in a certain way, lead scientist Thomson to conclude that this has to be not a ray, not a form of energy, but it has to be particles. And what Thomson does is he changes out the cathode. He tries lots of different cathode materials, lots of different metals. And he gets the exact same sort of result. No matter what kind of metal he uses, you get the same sort of glow. And what that leads Thomson to conclude is that this must be some intrinsic part of the atom. That there must be something inside the atoms that are consistent across all elements. What are called, or come to be called, electrons. Thomson comes up with what we call the plum pudding or raisin bun model for the atom. He postulates a sort of positively charged background material in which are tiny bits of negative charge, tiny bits of negativity, negative matter, that are embedded in the atom. The electrons are embedded in this positive matrix. This is, a stunning change. The last 100 years, Dalton's law model has been pretty consistent, pretty popular. The idea that atoms are indestructible, that you can't split them apart, that the atom is sort of the fundamental piece. To have that sort of overturned by realizing that there's something that must be inside the atoms, pieces that we can knock out using electricity, means that the whole system is quite a bit more complex than people originally thought. And this is an area where a lot of research needs to be done to figure out how are these things arranged inside here. What else? What is this positive stuff? Okay? And so in about 1897, 1896, we see this development of electrons and stuff. The other thing that's discovered at around this time is radiation and radioactive materials that produce radiation. In particular, a type of particle called an alpha particle. There are three main types of radiation. There's alpha particles, beta particles, and gamma rays. So alpha particles are simply helium nuclei, 2 protons and 2 neutrons bound together. Nobody knew this at the time. But they're heavy, they have a lot of positive charge, and they're sort of the perfect tool for trying to look at what's going on inside this atom. So we talk about sort of the next step as being the use of this radiation in 1899 through about 1910, 1911. Rutherford, an English chemist, working with a couple of other guys, but he's the sort of main researcher, do a bunch of experiments with shooting alpha particles, alpha particle radiation, at really thin gold foil. So gold is a nice metal for this because you can get it very thin. And they want a nice thin sheets because what they're trying to do is they're trying to shoot these alpha particles into the gold foil and see how they bounce or bend off. And the fundamental idea here is that if I take an alpha particle that has a positive charge and I shoot it through an atom, well, the positive charge in the atom should deflect or cause the alpha particle to bend. And how it bends tells us how much positive charge, where it's located, the size of the atoms, things like that. So the sort of classical experiment here is what's called the Rutherford gold foil experiment. And so we have a piece of a radioactive source and a gold foil, really thin piece of gold. And this is a screen that will glow or fluoresce when alpha particles hit it. So they take this source and they put it in a lead box with a tiny pinhole so the particles come out nice and straight. The particles smack into the gold. Most of them go pretty much straight through. Some of them are deflected a little bit. Some of them are deflected a lot. And the crazy, crazy thing is that some of these particles bounce way back, almost straight back to the source. If you're looking at a Thomson sort of plum pudding model, that shouldn't happen. Okay? There should not be any place enough positive heavy charge to bounce one of these big. These alpha particles are heavy, okay, and relatively fast moving compared to the other stuff that people were used to. At the time, Rutherford said that this was so crazy, it's as if they fired a cannon at a piece of tissue paper and had the cannonball bounce back. It completely blew them away, and it took them quite a while to figure out how they could explain what was going on here. But the only way you can reasonably explain what's happening here is if you have the most of the mass of an atom and its positive charge concentrated in the middle, concentrated at a very small point. And that point is actually significantly smaller than the atom itself. That's the only way that you could explain the angles that they were seeing and the bounce back effects that they were seeing. So that central point in the atom where the mass and the positive charge is was christened, was called the nucleus. Okay? And we now know that the nucleus has all the positive particles, all the protons, and all of the neutral particles, all the neutrons. And those two, the protons and the neutrons, make up nearly all of the mass. The electrons, Thomson's electrons, the little negative guys, are much, much smaller, much lighter than the protons or neutrons. And they seem to be spread out throughout the atom in some way that we're going to talk about later. So we have protons, neutrons, and electrons. Those are the fundamental particles that make up the atoms that we're going to study. Those are the particles that we need to keep track of. Okay? Some of those particles can be broken down even further. We're not going to worry about that in this class. That's a whole different realm of what's going on. And in fact, even the nucleus itself is only interesting to us by and large for how many protons and neutrons are there. Not the kind of weird interactions that can take place inside the nucleus. Although we will talk about that a tiny bit. So, what we need to be able to do fundamentally at this point right now is we need to be able to do a little bit of bookkeeping. We need to be able to keep track of how many protons, how many neutrons, how many electrons. And so we'd like to have some kind of notation to keep track of these things. Okay? So we use what we call atomic or isotopic notation to do just that. Here is an example of a symbol. Yes, I will move this. Not super happy with these boards. I'll have to look for a different solution. Maybe I tape a piece of paper up. I just need a flat surface. Yeah, I was thinking about that. This is just too high up and too far away. I like to point at things and do stuff. So we'll see. All right. So atomic notation. Here's an example. How many people believe that they have seen this type of notation before? Okay, most people. That's good, because you're supposed to have seen this before. But it's very straightforward. So if you haven't or you've forgotten that you've seen this, no worries. This symbol is the symbol we use to represent different elements. Each element has a 1 or 2, or in rare cases, 3 for the really unnamed ones, letter abbreviation. So 1 or 2 letter abbreviation. C stands for carbon. C stands for carbon. Okay? You need to know the names and symbols of all the elements. The reason being is that the periodic table that they give you on the AP test has no names on it. It only has symbols and a bunch of numbers that you need, but it doesn't have the names of the elements. So names and symbols of all the elements. In particular, the first 40 or so. I knew there was a reason why I had. Okay, I'll bring in a good periodic table for us in a little bit. But the first 40 or so elements, you really need to know. Those are the ones that we use most often. I'm going to give you some memorization stuff starting tomorrow. But start making yourself up some flashcards, names and symbols for all the elements. Some are more important than others. No? Oh, just scratch. No worries. The IB test is a little bit different. And so if you're only taking that, you still need to memorize them because you don't have time to look all these things up when you're going through and doing the test. But the IB test is structured a little differently in terms of what materials they give you. They give you a lot more material. Well, there are trade-offs to each class. So I'm trying to cover the core material here. All right, so names and symbols. What's the symbol for oxygen? Oh, great. How about potassium? Yeah, K. It's a tricky one. I mean, there are a few like that where it's just like, what? But it all comes from old Latin or Greek names. So, for instance, tungsten. Yeah, W. Because its old name started with a W. But we call it tungsten. Or, I think, wolfram or something like that. Not sure. Anyway, the symbol tells us what element we're dealing with. There's another way to know what element you're dealing with because what defines different elements is their number of protons. The number of protons in the nucleus defines what element we're talking about. Okay, that's the only thing that defines what element we're talking about. Because other aspects can change, like the mass of the atom, the number of neutrons, the number of electrons, those things change. But if you change the number of protons, you've changed what element we're talking about. So, carbon has 6 protons, and in its natural neutral state, it will also have 6 electrons. This number, this bottom number here, we call that the atomic number, tells us the number of protons and or electrons. So there are 6 protons and 6 electrons in a neutral carbon atom. The neutral there defines the fact that the proton's positively charged, and the electrons, did I say neutrons? That was wrong, very wrong. Electrons, the protons and the electrons we have the same number of them. And they balance out. Positive neutrons with the negative electrons balance out. In a neutral atom, 6 of each. Now, this top number, what we call the atomic mass number, is the sum of the protons plus the neutrons. So here, I know I have 6 protons. The sum is 12. How many neutrons do I have? 6. 6 plus 6 is 12. Okay? And it's as simple as that for figuring out how many protons or neutrons there are. Now, not all atoms of carbon have the same number of neutrons. Okay? Some atoms of carbon have more neutrons. We call this carbon-14. Okay? Carbon-14 is radioactive. It will decay. It will break down to produce nitrogen. Okay? One of the extra neutrons will decay into a proton and kick out an electron. Okay? We call that beta decay. Electrons are beta particles. Alpha particles, remember, were 2 protons and 2 neutrons, a helium nucleus. Beta particles, which we mentioned, are actually just electrons. Gamma rays are a form of light, a form of energy, very high energy photons. So we call atoms that have the same number of protons but different numbers of neutrons isotopes. Okay, so these are 2 isotopes of carbon. These are 2 isotopes of carbon. So this carbon isotope, carbon-14, is useful because of the fact that it does decay into nitrogen. If you start off with an initial sample of some amount of carbon-14, over time, the amount of carbon-14 will go down and the amount of nitrogen will go up. If you measure that, you can use that as a clock because the rate at which the carbon decays is very constant. So if you know sort of the starting point of the carbon, you can find out how old it is. Or if you assume this is how much I have now, you can look back and figure out how old is a sample. Now this works for organic material because organic material is full of carbon. So this is the carbon, carbon-14, that is used in radiocarbon dating. That's used to date organic objects in the tens of thousands of years old range. Okay? After a certain amount of time, the carbon value gets so small that it can't be measured accurately. Okay? The place where I worked this summer, the Center for Accelerated Mass Spectrometry, is one of the best facilities in the world for doing that kind of radiocarbon dating. Okay? And they can date stuff more accurately than any other facility on the planet. Really high resolution, really good ability to measure those kinds of things. And I'll try and talk about that in a little bit. Because measuring these isotopes is all about what I was doing over the summer. But we'll talk about that after you guys have some time to practice this kind of stuff. All right, so we know that if I've got 6 protons and the total is 14, that means I've got to have 8 neutrons. Okay? That tells me I have to have 8 neutrons. Now there's another thing that we can do here. If we think about, for a sec, if we think about an oxygen atom, okay, if we think about an oxygen atom here for a second, oxygen has 8 protons. How many neutrons does it have? 8 neutrons, okay? 8 plus 8 gives me the 16. Now, this -2 here in the upper right tells me the charge on the atom. So this atom is not neutral. This atom has a negative charge. We call that an anion. Anions are negatively charged ions. Talk more about that tomorrow. But the idea here is that the number of protons and the number of electrons are not the same. Knowing that it's oxygen, I know that it has 8 protons. But the whole thing has a negative charge. Electrons have negative charge. What this is telling me is that I have 2 more electrons than I have protons. That's how I can get a negative charge on the atom. So if I have 8 protons, that means I've got to have 10 electrons. 10 electrons, 8 protons leaves me a total of -2 altogether. Each electron has a -1 charge. Each proton has a +1 charge. Okay? So, if the protons and neutrons are balanced, then this value, that you don't write anything here. If you have more electrons than protons, you get a negative number. If you have fewer electrons than protons, you get a positive number. And you have a positively charged ion, what we call a cation. But this here is where we indicate the balance between the positives and the negatives. All right? All right. Take a sec right now on your notes. Fill in this chart. Copy down and fill in that chart. Yep, that's your example for today. All right. How many protons does a fluorine atom have? Remember this number on the bottom tells us 9 protons for that fluorine. How many neutrons? Where do I look? Top number tells me protons plus neutrons. Subtract out the protons from that, and we're going to have 10. 10 neutrons. How about electrons? What would change if the electrons and protons didn't balance out? Number on the upper right. This number on the upper right would change. Since there's nothing here, we know that it's neutral, which means that the protons and the electrons have to exactly balance out. All right, again, 13 right here means 13 protons. 27 minus 13 means 14 neutrons. Now, it says plus 3. What does that plus 3 mean? 3 less electrons than protons. So, instead of having 13 electrons, which would be balanced, I have 10. Notice, you cannot just start sticking in more protons. You couldn't say, oh, I must have 16 protons, because then you just change what element you're talking about. Okay? You vary the number of electrons to deal with charge. Okay? The number of protons stays the same. You vary the number of electrons. Now, we need to go through and deal with this one. How many protons? That's your starting point. 20 protons. That's our starting point because that's what's going to tell us 20. This is a calcium. The atomic number on this periodic table is this big number in blue in the upper left. Okay? 20 protons means we have a calcium atom. If I have 21 neutrons, what's my atomic mass number? 41. Protons plus neutrons. Now, is this a neutral atom? What tells me that this is not neutral? Protons and electrons are different. Do I have more positive charge or more negative charge? More positive charge. How much more? 2. So the symbol here, calcium, 41. We put the 20 and we put a plus 2. This indicates that we have 41 protons plus neutrons, 20 protons, and we're short 2 electrons. All right? Questions about any of this? All right. So, having passed her getting a basic understanding of atoms and the nucleus, isotopes, Jane, of course, has established a nice playroom with lots of lead shielding and a few radioactive warning signs. Fortunately, her dad brought his poker game down there into the playroom, and something unexpected happened. And now you know the secret to how Radioactive Man was formed.